Hello and welcome back, everyone. We are on Chapter 8 of Fundamentals of Inorganic Gases, third edition. Chapter 8 is divided into two lectures in this YouTube video series. The first lecture is on elasticity of glass, and then the second half of Chapter 8 is on hardness of glass. So next time we will be dealing with hardness, but today let us dive into the topic of elasticity. Elastic properties are one of the key sets of properties that differentiate a solid from the liquid state. So if you expose a solid material to a stress, the initial response of that solid material will be elastic, meaning that if you apply a stress, the solid is going to have some sort of constant deformation magnitude for a given stress. And as long as you are in that elastic regime, when you remove the stress, the initial deformation is recovered. So the material will go back to its original dimensions. On the other hand, a liquid exposed to a constant stress will have a constant deformation rate over time rather than a constant deformation magnitude, meaning that a liquid is going to deform through viscous flow, and that flow rate is what is linearly proportional to the applied stress. And so a solid will deform elastically and a liquid will deform through viscous flow. And dealing now with solid materials and their elasticity, if we have a glassy material and are at temperatures well below the glass transition, a solid is behaving mechanically or glass is behaving mechanically most like a solid material at those low temperatures, and glass can be considered as a linear elastic solid obeying Hooke's law. What is Hooke's law? Hooke's law defines a linear proportionality between an applied force and the elongation of a material, or a linear proportionality between the applied stress and the observed strain of the material. So for example, if you have a spring and if there is a linear relationship between the force acting on the spring and the elongation of that spring, then that spring is said to obey Hooke's law and is said to be linear elastic or Hookean. And it's the same thing with a material. If there is a linear relationship between the applied stress and the strain that is observed in response to that stress, then that material is said to exhibit a Hookean response or is linear elastic. Now, one can always come up with loading conditions that will violate linear elasticity, either moving into a nonlinear elastic regime, as shown here for some of the extreme deformations of the spring, or there could be a plastic yielding or fracture that occurs. But the initial response of a material to stresses, the initial response of that solid material would be Hookean. Now, we can define different types of elastic moduli that govern the proportionality between the applied stress and the resulting strain. If we start off with the case of uniaxial stress, so just having stress along one direction here, x, so if sigma sub x is the uniaxial stress and the resulting uniaxial strain is E sub x, the constant of proportionality between the two is the Young's modulus. And so if we plot stress versus strain as in the diagram on the right, and if we are in this linear regime, the slope of that curve gives us the Young's modulus. And the Young's modulus is going to have pressure units like gigapascals, so it'll be the same units as the stress because the strain, of course, is unitless. So that is the case of uniaxial loading, where you've got stresses applied along one direction. This figure here shows the application of uniaxial stress sigma sub x that is putting this material into tension, and the constant of proportionality. In that case, the particular elastic modulus of interest is the Young's modulus, labeled here with a capital E. Now, if instead of uniaxial stress, we go to biaxial stress, also known as shear stress, Now the stress has two subscripts here, for example, sigma xy. This is showing application of stress along two directions, which is what produces shear. The shear stress results in a shear strain, which is E sub xy. And now the constant of proportionality between the shear stress and the shear strain is, of course, the shear modulus, which is labeled G. So the basic equations here are the same. The only difference is that in the uppercase, in defining the Young's modulus, this is done under uniaxial loading conditions. And in this lowercase, for the shear modulus, the loading is done under biaxial conditions. Now we can take this one step further and go to triaxial loading, also known as hydrostatic loading or hydrostatic stress. In the case of hydrostatic stress, we've got the same stress applied along three directions. And so in this case, the sigma x is equal to the sigma y is equal to the sigma z. For hydrostatic stress, we can also call that the negative of the pressure. And so these applied stresses would be equal to minus P, where P is pressure. And if we make the proportionality constant here between the hydrostatic stress and now the hydrostatic strain, which is a volumetric strain, E sub V, that constant of proportionality is the bulk modulus of the material, which here is labeled as a capital K. There's one more elastic property that we care about in glasses, and that is Poisson's ratio. Poisson's ratio nu is defined as being minus the change of length of a material along an orthogonal direction to an applied uniaxial stress divided by the change of length along that direction. So if we consider this diagram here on the right, if you have if you are exposing this material to a uniaxial tension, and that uniaxial tension increases the length along that direction along which the stress is applied. If that increase of length is delta L, there's also going to be some change in length along the orthogonal direction, and that change of length is delta L prime minus the ratio of those two is equal to either minus the strain along the y direction compared to the x, if x is the loading direction, or you can write that equivalently as minus the strain sub z over x. This is what gives us the Poisson's ratio of the material. So this is telling us how much the material shrinks along the direction that is orthogonal to the direction of an applied uniaxial tension. And for most oxide glasses, the Poisson's ratio doesn't vary by much. For most oxide glasses, the Poisson's ratio is between about 0.2 and about 0.25. And it doesn't vary by too much with composition. Now, one of the nice things about glass that makes it a little bit easier to study compared to many crystal materials is that glass is isotropic, meaning that the properties are the same along different directions. And what this means is that you could change the direction of application of stresses, and the strain responses are going to have the same magnitude in response to those stresses because the directionality of the loading doesn't matter. And when we account for the isotropic nature of glass, what this means is that with the set of four elastic constants, the Young's modulus E, the shear modulus G, the bulk modulus K, and the Poisson's ratio nu, only two out of those four parameters are independent of each other. And that means that if you measure any two of them, or if you know any two of them, then you get the other two values for free. And we can get that through these relationships, which are valid for isotropic materials. So the shear modulus is equal to the Young's modulus over 2 times 1 plus the Poisson's ratio. This means if you're given the Young's modulus and the Poisson's ratio, you can calculate the shear modulus, or given any two of them, you can calculate the third. The Poisson's ratio is equal to the Young's modulus over 2 times the shear modulus minus 1. the bulk modulus is equal to the Young's modulus over 3 times 1 minus twice the Poisson's ratio. And the Young's modulus is 9 times the product of the bulk modulus and the shear modulus over 3 times the bulk modulus plus the shear modulus. So using these 4 equations, if you're given any 2 of these elastic constants, you can calculate the other 2. So 2 of them are all that you need, which means that this set of 4 elastic constants reduces to just 2 independent parameters. This, of course, is very helpful when we go about measuring the elastic properties of a glass. There are a couple of common ways to measure the elastic moduli of a glass. One of them is through a beam bending experiment. For example, this is a 3-point bending setup where you've got some rectangular prismatic beam of the glass, and it is supported in 2 places here, shown on either side. And then there is some applied load that is acting downward in the middle. So this is a 3-point loading configuration. And if the distance between those 2 outer supports is L, and then we can calculate what is the center deflection. This deflection is denoted by a small delta that is equal to the force, or this force acting downward here, F, times this separation distance of the supports, L raised to the 3rd power, and that is all divided by 48 times the Young's modulus, E, times this geometric moment of inertia, I, which is just given by the geometry of the beam here, where B, this little b, is the width of the beam, and the little h is the height of the beam. So given the geometry of the beam, that calculates the geometric moment of inertia. And then if you calculate the relationship between the center deflection versus the force, that can give you directly then the calculation of the Young's modulus of the material. Another actually rather straightforward way of measuring the Young's moduli of a glass is through resonant ultrasound spectroscopy, or RUS. With RUS, an ultrasonic pulse is propagated through the specimen. So this may be propagated, say, starting on this side. The pulse is propagated through the specimen. It's reflected back by the opposite surface, and then it is received as an echo. And what we can measure then is the amount of time that it takes the waves to reflect off of the other side and propagate back to where they began. This will give us the velocity of these waves that are propagated. And there are 2 types of waves that are propagated in the material. There are longitudinal waves and shear waves, also known as transverse waves. You can see the pictures here that show a transverse wave here on the upper right, and then a longitudinal wave here right below it. So if you measure the time that it takes and you know the distance for the wave to propagate to the other side of the material and back again, that will give you both velocities. So both the longitudinal wave velocity here, v sub L, as well as the transverse wave velocity, v sub T. And the Poisson's ratio, it relates to both quantities. So the Poisson's ratio nu can be calculated based on this ratio of the transverse wave velocity to the longitudinal wave velocity using the formula shown on top. And then the shear modulus can be calculated just based on the square of the transverse wave velocity along with the density of the material rho. And so given these 2 velocity measurements, the velocity of both the transverse and the longitudinal waves, you can calculate both the Poisson's ratio and the shear modulus of the material. And this can be done very accurately and very quickly. Any errors might be due to pores or cracks of the material, anything that could act to reflect the ultrasonic waves prematurely. But since glass is isotropic, once you have two of these elastic constants, so knowing the Poisson's ratio and the shear modulus, we can go back to these equations and get everything else. So if you know the Poisson's ratio and you know the shear modulus, you can immediately get the Young's modulus. And using that Young's modulus and the Poisson's ratio, then you can get the bulk modulus after that. So you can easily get all four of those quantities based on this resonant ultrasound spectroscopy measurement. So now let's go into some typical values of elastic moduli for various glasses, starting with our good friend vitreous silica, SiO2. The Young's modulus of vitreous silica, E, is about 70.0 gigapascals. The bulk modulus is 37 gigapascals. The shear modulus is about 35.5 gigapascals. And the Poisson's ratio is actually very low for silica. It is much lower than most other oxide glasses. The Poisson's ratio is 0.17. Now, if we add a modifier to silica, for example, if you add lithium oxide to silica and measure all of these elastic properties as a function of the lithium added to the system, what you can see is that there's not really a huge change in these elastic moduli. There is a very slight increase of the Young's modulus with added lithium oxide, meaning that it would take slightly more stress to get the same amount of uniaxial strain. This could be due to the lithium ions occupying some of the open spaces within the silica glass network. The bulk modulus likewise is increasing by a small amount for the same reason. The shear modulus really isn't affected very much at all by the incorporation of lithium. And you can see that the Poisson's ratio here in nu, this is Poisson's ratio multiplied by 100. So you have to take this number on the y-axis and divide by 100 to get the Poisson's ratio. It is around 0.2 or a little bit above or slightly below 0.2 across these. This slight change of Poisson's ratio is due to the shear modulus here being relatively constant because the transverse wave velocity is relatively constant. Apparently, it is mostly the longitudinal wave velocity that is changing here. So there's a relatively constant shear modulus with a slightly changing Young's and bulk modulus, and that is all captured in this changing Poisson's ratio. What about for sodium silicate glasses? If we add sodium silicate to these systems, the Young's modulus is actually decreasing ever so slightly instead of increasing. Presumably this is due to having a greater, so the sodium is not just filling in open spaces, it's kind of increasing the molar volume of the glass network itself, while also creating non-bridging oxygens, and that is acting to create more strain for a given amount of stress, which means that the Young's modulus here is actually decreasing slightly with increasing sodium content. The bulk modulus is increasing, so it's having an opposite direction because of the sodium atoms being more difficult to compress if you're under hydrostatic compression. The shear modulus is decreasing slightly. This is presumably due to the formation of non-bridging oxygens, and putting that all together, the Poisson's ratio is increasing slightly. So it's going between about 0.2 and 0.25 for these sodium silicate systems. It's a very similar story with potassium silicate glasses as with sodium silicate glasses with respect to all of these changes in the elastic coefficients. What about the effect of dye balance? Supposing that you have a compositional series, which is sodium oxide with X amount of some divalent oxide and some amount of silica here. What we have is, as we're increasing X, we're increasing the proportion of these divalents. And you can see that the smaller divalent here, beryllium oxide, leads to a greatest increase of the Young's modulus. Calcium and magnesium also lead to an increase of the Young's modulus, strontium, zinc as well. Lower increase for these larger divalents like cadmium and barium. And if you go super large, it actually changes and goes in the opposite direction, with lead oxide, the Young's modulus is going down. So you can see what happens here with the, generally speaking, the modifiers that have higher field strength are going to act in a more positive direction, and the ones with a lower field strength are going to act in a more negative direction. This shows the variation of Poisson's ratio for each of these oxides as well. But these smaller modifiers that have the higher field strength tend toward higher modulus compared to the larger ones. Now, bunch of interesting papers were published by Tanguy Roxel from University of Rennes in France, and he was looking at elastic recovery of different glasses as a function of Poisson's ratio. And here are some typical values of Poisson's ratios for various glasses. Silica having a very low Poisson's ratio of about 0.17, Pyrex borosilicate glass being just above 0.2, soda lime is a little bit higher. Most of the silicate glasses are in this range of 0.2 to 0.25. Oxynitride glasses with higher conductivity was actually pushing that a bit higher. And interestingly, bulk metallic glasses can actually cover a really wide range, but the one plotted here has a Poisson's ratio of 0.4. So we note that most silicate glasses have Poisson's ratios less than 0.25. Metallic glasses can achieve especially high values of Poisson's ratio. In the limit of Poisson's ratio going to 0.5, that indicates incompressibility. And so bulk metallic glasses aren't going all the way, but they are moving in that direction compared to typical silicate glasses. So to summarize today's lecture on elasticity of glass, elasticity is a property of solid materials that describes their stress-strain response. The elastic response of a material is elastic because it is recoverable. So if you apply a stress, there's a strain in response to that stress. The amount of strain, the magnitude of that strain is governed by the appropriate elastic modulus. And then as long as you are in that elastic regime, if you remove the applied stress, then that strain is recovered. Most glasses at temperatures well below the glass transition are in fact linear elastic, which means that they are described well by Hooke's law. For an isotropic medium such as glass, only 2 out of these 4 elastic constants are independent among the Young's modulus, shear modulus, bulk modulus, and Poisson's ratio. Elastic moduli can be measured through stress-strain curves or ultrasonically. Next up, we will be taking on the second half of Chapter 8, which is all about the hardness of glass. So I will see you next time. Thank you again for joining.